damping. Okay, so damping is also important. You can understand damping both theoretically as well as mathematically, but it's a very interesting concept that we usually have. So before we actually go to the idea or the mathematical derivation of damping, it's important that we develop a basic concept for this. Okay, so what happens usually is that whenever we are basically considering the motion, a simple harmonic motion rather, and if it is periodic in nature, we are going to see that this is the waveform that we are going to have. Now every time you look into this waveform, you see that at every point the amplitude is a. Here also it's a, here also it's a, if you're drawing it correctly, here also it's a. Okay, and in general the intensity that we have, intensity, I hope you understand, for example, the intensity of light falling on a particular surface, okay, that intensity is actually proportional to a square. And what does intensity mean? Intensity is directly related with energy. Okay, more intense means that light is carrying more energy. Intense means if the intensity is high, a particular point or a particular area will get heated up. That means it is directly related with energy. So that means if intensity is proportional to a square, that means the energy is also proportional to amplitude square. But if something is traveling from one point to another, there will definitely be some kind of loss. So it's not that at every point you are going to have the same amplitude. At every point having the same amplitude is practically something which is difficult. So when we are having the amplitude initially something like this, and as we keep going ahead, we'll see that this amplitude will keep on reducing. Okay, this amplitude will actually keep on reducing. Just a sec. Yeah, so the amplitude keeps on reducing. So what does it say? It says that the energy will reduce, because I said that energy is proportional to amplitude square. In a way, the energy is also getting reduced. That means there is dissipation of energy. Okay, the energy loss is definitely there. So this particular phenomenon where we are actually seeing that the energy is getting lost as we progress, or the amplitude keeps on reducing, is actually called damping. So this is the basic idea behind damping. Now practically, if you want to look into it, if you are just taking a pendulum, okay, and if you are not applying any kind of external energy, and you are just taking it here and then you are going to leave it, then what happens is the pendulum is going to swing to and fro, and eventually it is going to stop. Eventually it is going to stop. So what does it mean? That there is damping, there is reduction of amplitude with time. Now if you are having a watch, okay, where those old kind of watches where you are actually having a pendulum, okay, nowadays modern watches, what they have is they don't have this keying thing. You don't have to key it for the pendulum to work. You just put a battery, that's it. So if you're putting a battery, or you are keying it, okay, it simply means that you are giving an additional energy for the pendulum to work, and that is why the amplitude of the pendulum will be the same until and unless the battery runs out. So if the amplitude is zero, that means the battery is zero, there is no external energy. So in that kind of oscillation we call it as forced oscillation. This oscillation that we said, actually it happened naturally. Okay, so if we are basically talking about frequency, if we are talking about frequency, there are two kinds of frequencies. Okay, okay, this is in another sense the two kind of frequencies that I'm saying. The first kind of frequency is actually called the natural frequency of the body. So any object will actually have its own natural frequency. Okay, and another one is the external, or it is forced. Okay, it's a forced oscillation. So basically we are basically going to have an external frequency, so it is not a natural frequency. Okay, so natural and not natural, we can say, let's say. So not natural means you are going to have some kind of forced oscillation here. Forced oscillation. So if you're talking about a swing, you are seeing that as soon as it comes to one extreme position, you again push it, and you keep on pushing it. Okay, you are giving an external force every time. So that means that's not the natural frequency with which it vibrates. But imagine a string here, okay? If you're imagining a string, you are plucking the string. Let's say you're plucking it only once, and you plug it and leave it, and then it will keep on vibrating. The frequency with which it vibrates after you leave, and it does not have any kind of external force acting on it, is actually called the natural frequency. But if we are having a force which is always connected with this, that means you're keeping the amplitude constant by giving an external force. That means this is not a natural frequency, it's a forced oscillation kind of thing. So the approach for solving problems on forced oscillation, okay, and unforced oscillation or natural oscillation, the approach is kind of different mathematically, okay. So we're just going to look into this. So the idea of damping is very simple, that if we have the amplitude A, with time it will keep on reducing. That's the idea, okay. So now let's imagine a situation, okay. We are imagining a situation here. Let's say I have a spring system, and it is connected with a mass m, and I'm keeping this spring inside, let's say, some water, okay, some water, air also we can consider. But the thing is, the air, in air, the opposition force because of which this spring will stop will be kind of low. But if we take it in water, this will be very high. It simply means that if this keeps on oscillating because of the frictional force or the viscous force of water, this oscillation will stop faster compared to air, okay. So that means that there are two kinds of forces acting on this system. The first force is what we call as the restoring force. That is also a negative force because it does not allow the oscillation to happen easily. So that is actually called the restoring force, which is negative. And it also has another force which we call as the drag force. Okay, we call it as the drag force. Now, what do you mean by drag force? So you can imagine a simple situation. Let's say I have got a bucket of water, okay, and you have a bucket of water and you have a mug, and you just want to take out water from this using this mug, okay. Now, if you take the mug very slowly and take out the water, you are not going to feel any kind of force offered by water. There is no kind of force, okay. But if you do it very fast, okay, if you do it very fast, what happens is this water body will also offer some kind of opposition force, okay, and that force is actually called drag force. That drag force, okay. So that means the oscillation of this particular mass will slow down because of this force as well, okay. So this is the damping force that we are talking about, or in this case we can also call it as the drag force. And the second force that it is coming working on it is the restoring force. So drag force and restoring force, and if we combine them together, if we combine the damping force and the restoring force, we are going to get something which we call as the net force, okay. So the net force is actually a very important factor, okay. Now, what are the, how do you write it down mathematically? It's simple. If we consider the restoring force, it is minus of kx, because we know restoring force is proportional to x and the constant is minus of k, okay. But please do remember that k, we have already seen, is nothing but minus m omega square, okay. So this is important, okay. Sometimes when we do numerical, we'll need this, okay. If you want to find out, let's say, the frequency of oscillation, and if you know what is the spring constant of this particular spring, we can simply write it down as root over of k divided by m. So this is a very important relation. More or less we might use it later as well, okay, for doing numericals. तो ये मेरा हो गया frequency. So this is my frequency, and I can relate it with the force constant. So what happens is that if the spring is very tight, this force constant will be high, okay, and if the spring is loose, the force constant will be low as well, okay. So these things we can check later, okay. Next is the drag force. So as I said, this drag force actually depends on the velocity. So the drag force is proportional to velocity, but the force is opposite to velocity. More the velocity, more would be the force. So it will not allow the mug to come in and take out the water that easily. So that is offering an opposition force. That's why there is a minus sign. And we have to bring in a constant. Let's bring in a constant and name it as b. That's it. So you've got minus kx minus b, and then we have got the net force. The net force acting on the system is mass into acceleration, and acceleration is something which we know is nothing but m into d2x dt square. Okay, so d2x dt square, if we write it down, we can actually get what is my acceleration. Okay, so now we can write down an equation. We can form an equation very easily. F net is equal to restoring force plus drag force. F net is m d2x dt square minus kx minus bv, which is equivalent to m d2x dt square plus. Now if you look into this, b, I can take it that side, so it will be plus b. And what is velocity? Velocity is dx by dt. So I'll write it down as dx by dt. And this is minus kx. I'll take it on this side. This will become plus kx. Okay. Now what we have is a second order differential equation. Okay. We have a second order differential equation, and we can try to simplify this further and solve it. Actually, the solution is not very complicated, but obviously it's a bit long. Okay. So let's see. We will try to. I will give you the results here. The maths is not very difficult here. Dx dt square plus, let me divide throughout by m, so I'll write it down as b divided by m into dx divided by dt plus k divided by m into x is equal to 0. Okay, so we can write it down like this. But if you look here, we have already seen it. We can actually replace it here. If I write it down as k by m, this is minus omega square. Okay, so we'll ignore the minus sign for now. We're just going to look into the constant value. So it is omega square. So k by m can be written as omega square. Okay, so k by m, we're going to write it down as omega square. So what we can do now is I can simply write it down as d2x dt square plus, now this b by m, again I will take it to be a constant. I'll take it to be 2 beta dx by dt. I'm writing it down in such a form so that we can easily solve the second order differential equation, plus this is omega square x is equal to 0. Now the aim is actually to solve this equation. Okay, and the aim is actually to solve this equation, and this is actually a second order differential equation. There are different ways of solving the second order differential equation. One of the solution is actually considering a trial solution. So we can actually consider a trial solution for this. That means that I will consider the solution in such a way so that if I put it here for x solution, what does solution mean? Solution means that what should be the form of x, so that you put it here, and when you add all these terms, you should get 0 on this side. Okay, so we are going to consider something like this. So the trial solution that we are going to consider, this is something which you have to remember. Everything else is more or less pure maths. X is equal to c e to the power alpha t. We don't know what is c, we don't know what is alpha, these are just constants. So eventually we can see that we can actually find them. In fact, it will actually show the dependence of the different values here. Okay, so trial solution is this. Now what I need is x. I also need x dot, that means velocity. I also need x double dot, that means this term, acceleration. Okay, so in order to understand this better, what we can do is we can simply say that x dot is nothing but d dx of this. So this is c e to the power alpha t, so I can take it as alpha and e to the power alpha t, right? That's my x. And then I can take x double dot as well. Okay, x dot and now x double dot. Okay, if I do the differentiation again for this, c will be there, c will remain, and e to the power alpha t, alpha is already there, one alpha is already there. E to the power alpha t, if you differentiate, you will get one more alpha, so it is alpha square e to the power alpha t. Now you've got x dot and x double dot, and what we can do is we can replace it here. Okay, so d2x dt square, dx dt and x all will have the term c e to the power alpha, c e to the power alpha t, c e to the power alpha t. So what we can do is we can simply take c e to the power alpha t out, and within the bracket, for the first one we will just have, it's x double dot. The x double dot is c to the power 40 alpha square, so I can simply write it down as alpha square, okay, plus we have got 2 beta, 2 beta is already there, into, now this is dx by dt, so it's x dot, so c to the power alpha t, we have taken it out, so we can write it down as 2 beta alpha plus, and then this is just omega square, we can simply write it down as omega square is equal to 0. Oh, that's an x is c to the power alpha t, we have already taken it outside. Now you see this equation will have a solution if c to the power alpha t is equal to 0 or this entire term is equal to 0. That means it's a quadratic in alpha, and let's say I can find out what is the value of alpha here. Alpha square plus 2 beta alpha plus omega square is equal to 0. The only unknown term is alpha. We know beta, that's directly connected with the damping constant and the mass. We know what is omega square, it is with the spring constant and the mass. So that's simple for us. We are just going to solve it for alpha. Now you can easily solve it for alpha, by using the quadratic equation example. So if you look into alpha solving, let's say I'll solve it. This alpha is equal to minus b, so we have got it here as 2 beta, so I will take it as minus b as minus of 2 beta plus minus root over b square minus 4ac. B square means 2 beta square, so I can write it down as 4 beta square minus 4a. If you look into this equation, a is here, so that's just 1 into c. C is omega square, so it is 4 omega square divided by 2a. A is 1. Okay, so we can actually write it down like this, and if we simplify it further, I can separate it out. Minus 2 beta by 2, so I can just write it down as minus of beta plus minus, we can take 4 outside and there will be 2 here, so these 2 and this 2 will get cancelled out, so I'm not going further. I can just simply take it like this. This is beta square minus omega square. So this is my solution. And what solutions we have? We actually have got 2 solutions here, okay, and if you have 2 solutions, we can combine them and see what will be my final result. Okay, so what was my trial solution here? X is equal to c e to the power alpha t. Okay, so therefore we can use this trial solution and write down the general solution. General solution, it's not difficult, okay, it's all about simple maths here. Okay, general solution. Now if you look into the general solution, this is my x, so I will write it down as that x is equal to c. Now you see there are 2 here. This is minus beta plus root over beta square minus omega square, and minus beta minus root over beta square plus omega square. So I will take 2 different terms and then combine them. So I will take, let's say, one constant is c1. This is the general solution. E to the power alpha. Alpha is this. Let me just take it like this. This would be minus of beta. And remember there is a t here. So I'll multiply t with all the terms. So it is minus of beta t plus, let me write it down it for better legibility as beta square minus omega square whole thing to the power half into t. So this is one part of the solution plus c2 e to the power minus of beta t minus beta square minus omega square whole thing to the power half into t. So this is what we call as the general solution. Now this general solution is important. We are going to use the idea of general solution to look into certain scenarios. Okay, now what are the possible things that might happen? This will actually give me an idea. I'm not going to give you the entire solution for this, so don't worry, you'll not need it. But at this point of time, let's just look into the possible scenarios. Possible scenarios. So if you look here now into the possible scenarios, what does it mean? It simply means that there are certain terms here. One is beta, one is omega. Okay, and if we recall, what is my beta? Beta is equal to b divided by 2m, and omega is equal to root over of k by m. So this beta that we have is connected with the damping force or the drag force, and this k or omega, which is depending on k, is connected with the restoring force. Now there is always a competition between this damping force and restoring force, right? What happens is, if the damping force is more, then the oscillation would be less. If the restoring force is more, then also the oscillation would be less. Okay, it is trying to bring it to its original position. So if there is a balance between these two, the oscillations will be more or less there. Okay, so the possible scenarios are something which decides whether there would be uh, oscillation, whether there would be damping, whether there would be both damping and oscillation. Okay, what does it mean? In damping, there won't be any kind of oscillation, there will be only damping. That means whatever was the amplitude originally, it is going to die off. That's it. And when we are talking about only oscillation and no damping, that means it's just going to oscillate. There is not going to be any kind of reduction in the amplitude. And when we are talking about both damping and oscillation, that means there is going to be oscillation, amplitude is also going to be there, but then this amplitude will slowly die off, which is, this is very important. This is very much needed in our practical life as well. Okay, there will be oscillation, but eventually it is going to die off. So based on that, we can actually have four possible scenarios. The first scenario is, we are going to look into the scenario based on this particular relation. The first scenario is beta is equal to 0. Okay, so when we put beta is equal to 0, we can actually simplify this equation and check whether we are going to have damping, whether we are going to have oscillation, or both damping and oscillation. Okay, and when we actually check it, we are going to see that if beta is equal to 0, we are going to have simple harmonic motion. That means mostly we are going to have oscillation. Okay, you can think about it in like this also. If beta is equal to 0, that means this is 0. If this is 0, that means there is no damping force. If there is no damping force, that means there is only restoring force. Now if you pull it and you push it back, every time if it goes back to the same position, it is going to come back to the same position on the other side. The same kind of potential energy is going to get stored, and it is going to get converted into kinetic energy, potential energy, kinetic energy, and is going to oscillate forever, oscillation. Okay, but if there is some loss of energy, then only the chances are that the oscillation will reduce or die down. Okay, so obviously there is some loss of energy, but we are going to see that later. So this is the first condition when beta is equal to 0. Okay, beta is equal to 0 means b is equal to 0. That's it. The next condition is, if you look into this comparison, beta and omega both are taken inside the same bracket, so we can say this beta square is less than omega square. Okay, this is the second condition. Now this is something which we are going to have, and we are going to have an oscillatory motion. Okay, oscillatory motion, oscillatory motion. Okay, and this actually has got a specific name involved. This is actually called underdamping. Underdamping. Okay, the third condition is, obviously I think you can guess it from here, beta square is equal to omega square. Both may be equal as well. That means whatever is the restoring force, equivalent is the damping force. Okay, if this happens, then you can actually guess also there would be no oscillation. No oscillation. No oscillation means we simply say it is a critical damping. Critical damping. Critical damping is which divides the under damping and over damping. Okay, critical damping. And finally, the fourth possible scenario is beta square is greater than omega square. So beta square is greater than omega square means damping force is much greater than the restoring force. That means you are not going to get any kind of oscillation again. Okay, no oscillation, no oscillation. But this time we don't call it as critical damping or under damping. We call it as over damping. The damping does happen here as well. So these are the four possible scenarios when we are actually solving this and putting the values. Okay, we can also think about it in like this. Let's consider beta square. Beta square is nothing but b square by 4m square. So if I write it down as beta square is equal to omega square, it simply means beta mane b by 2m, so it is b square by 4m square is equal to omega square, and omega is k root k by m, so omega square would be nothing but just k by m. This will actually give me a relation between b and k. Okay, you can cancel out these terms. That means b square is equal to 4km. So whether you say beta square is equal to omega square or you say b square is equal to 4km, more or less both will mean the same thing. So in this particular condition we can say b square is less than 4km. In this condition we can say b square is equal to 4km, and in this case we can say b square is greater than 4km. And based on these four situations, we can actually decide whether there is oscillation, under damping, critical damping, or over damping. Okay, and that's the most important part. So what happens is that if we actually try to solve it, we are not going to solve it, but just going to give you a brief idea of the scenario that we actually might have. Okay, so if you are considering the first condition, okay, you are just going to get oscillation. Okay, the first condition you are just going to get oscillation with no damping, something like this. That's my first condition. Okay, number one. If you look into the second condition, okay, that's oscillating motion, but then there would be under damping as well. Okay, there is going to be a decay as well, so you are going to get this, but eventually this is going to die off. Okay, so that means you are going to get something like this. So whenever we are actually having an oscillating term, whenever we are actually going to have an oscillating term, it is starting from the origin and it's a periodic motion. That means you are going to have an equation where we'll be actually having a sine term or a cos term as well. Cos is also something which is related with periodic motion, so sine term. So if you solve this for this first condition and you put b is equal to 0, so beta is equal to 0 here, 0 here, this would be minus omega square root omega square, so there will be an imaginary number, and if you solve you'll get the sine term for this. Okay, at the same time here we do have the sine term, which is because of this, but the amplitude is reducing. That means there is also a term which is called the modulating term. Our modulating term means we are actually going to have an exponential term. So when you solve it for the first one, you are going to get only a sine term. For the second one, you are just going to get the sine term along with an exponential term. That means it is oscillating at the same time with a reduction in amplitude is also observed. Okay, that's the first and the second case. In the third case and the fourth case, both are same. Okay, we are going to see damping. Of course, one is going to damp faster than the other, but let's not discuss this right now. We have only damping in 2 and 3. Sorry, 3 and 4. So this is going to have only damping. Okay, only damping money, we are just going to get exponential term. That's it. If you solve it, you can try it also. Okay, it's not very difficult. Check this. Beta square is omega square. So you take beta square omega square. This part will become 0. Take this. This will also become 0. C1 and C2 are constants. This is just e to the power minus beta t, right? So if you consider it for the third case, if you take everything to be 0, you're going to get x is equal to C1 e to the power minus of beta t plus 0, then plus C2 e to the power minus beta t. So you're going to get 1 beta t e to the power minus beta t. So this is e to the power minus of beta t C1 plus C2. So the third case is very simple to analyze. See, there is only an exponential term. There is only damping. Exponential term mein, if you actually want to plot an exponential graph, and if it is e to the power x, that means with value of x, e will increase. So you're going to get a graph something like this. Okay, but on the other hand, if you are actually going to have a value which is e to the power minus x, then the graph would be like this. That's it. Okay, this is e to the power minus x. Okay, and this is e to the power x. That's it. तो यहाँ पे देखो, it's e to the power minus x, so it is decay, so obviously this is going to decay. You're going to get a graph something like this. Okay, so this is the entire idea about damping.